Okay, hello everyone. Uh, First of all, I'm taking this video because I had a terrible mistake in the previous lecture. So especially I had a terrible mistake on explaining the Hill-Huntington method. So instead of my lecture, please see this video again, and it won't take a lot of time. So let me explain what I had mistake and how can I correct it. So let's see the lecture note again. So then, yeah, when I explained the third step, so when you found this rounded quarter, what I explained in the class was that it is just rounding the Q star, right? However, that was wrong. That was wrong. Instead, what you need to do is that this rounded quarter is determined by following decision. So if your Q, exact Q is greater than Q star, then or equal to Q star, then round Q up, but which is just, side of the Q. But if Q is less than Q star, then round Q down, which is say plural of the Q, right? So instead of rounding Q star itself, we use Q star as a reference. So if our Q is greater than or equal to Q star, greater than or equal to Q star, then round it up. But if it's less than Q star, then round it down. So let's deal with the examples again. So here again, if you just calculate Q star, actually Q star is the same, then what you can get is root of 3 times 4, which is 3.4641. So this part you don't need to change it from the previous lecture note. It is just same as this one, but I intentionally just delete it. And so this part is just same. And then you can see the original numbers. Then first line, Q is less than Q star, but second line, Q is greater than Q star, and third line, Q is greater than Q star. Even if it is less than 1.5, but this Q is greater than Q star. And the third line, Q is less than Q star, and fourth line, Q is less than Q star. So for lines which has Q less than Q star, just round it down. So what you get is 3, 18, and 17. But for lines with the Q greater than Q star, you need to round it up so you can get 6 and 2. And if you add all the number, then you will get the 46. So in this case, every 6 is just distributed well, right? Okay, then go to the next question. So here, the adjust divisor is the same as standard divisor because we do not change any divisor at all, right? But in the next example, here again, you can calculate Q star, just leave your Q star calculation from the lecture. It is just same as what you did in the lecture. I just write down it quickly. And then if you compare Q and Q star, then in case of the first line, Q star is greater than Q. But in case of the second line, Q is greater than Q star. But in case of the third line, Q is greater than Q star, and for other lines, again, Q is greater than Q star. So the rounded quarter should be, for the first line, it should be 3 because we need to round down, right? But for other lines, we need to round it up. So what you can get is 3, 2, 1, 1 here. And if you add all the numbers, then you got 10, right? So we need to make this 2/6 should be reduced, right? Thus, in next case, we need to calculate di minus, which is population over square root of ni times ni minus 1 instead of ni plus 1 here, right? And if you calculate this number, then for the first one, it is 3,862 over square root of 3 times 2, and it is almost the same as 1567.65, and the second line 2818 divided by 3 times 2 is 1150.44, and 1881 over 2 times 1 is almost the same as 1313.07, and 500 divided by 0 is, is infinity, and 21 divided by 0 is also infinity, right? But in case of the inverse, the minus, you need to choose the divisor which are the smallest one instead of the greatest one. And here, among all divisor, the smallest one is the second one, right? So in this case, you need to get rid of the 1/6 from here. So the adjusted seat should be 3 is the same, 2, 1, 1 is the same, but it should be choose to 2, right? Then again, you need to calculate divisor again, because if you add all the number, then still is 9, which exceeds the of house, which is 8. And if you just calculate divisor again, then what you can get is the all numbers in the except the second line should be the same. But in case of the second line, it should be calculated again. So now this one should be 2818 divided by square root of 2 times 1, and it is almost 1992.62. So the next smallest one should be the third one, right? So in that case, the adjusted seat should be 3, 2, 1 here, and 1, 1. 1, 1 just the same. So, and finally, all six are remaining as, 3 to 1, 1, 1. And still you can see that Hill-Huntington method is favored for some smaller stage, right? Because in case of the smaller number, they always round it up instead of rounding down, right? Okay, then move on to the next example. So here, again, Q star is the same as in what we did in the class. So if I just recover it, then it is just here. (4952) and 2949576. And 1 times 2 is 1.414 something. So if you just compare Q and Q star, then for the first line, it is less than Q star. And for the second line, it is greater than Q star, so round up. And for the third line, it is still greater than Q star, so it round up. For the first line, it is also greater than Q star, so round up. So if you all round up, then when you can get rounded quarter is, except of the first line, one you can get is 27 instead of 26, 30 instead of 29, and 2 instead of 1. And if you add all the numbers, then what you can get is 101. So we need to reduce one seed from this Hill-Huntington method. So we need to calculate di minus, and di minus is population of I over square root of apportionment times apportionment minus 1. So here, first one should be 5565 over square root of 42 times 41. And this is almost same as 134.106. And next one should be 3471 divided by 27 times 26, which is almost same as 131.004. And 3864 divided by 3929. And if you calculate it, then it is almost same as 131002. And the last one, 197 divided by 21 is almost same as 139.3. So the smallest one should be the third one, right? So you need to get rid of one seed from the third row. So the adjusted seed should be, the all other seeds are the same except the third one, right? And if you add all of them, then you get 100. So here the adjusted divisor is 131.002. Right? Okay, then let's go to the last example. So here again, just calculate Q star your geometric mean as usual, what we did in the class. Then what you can get is the same number as we did in the class. So I will just fill out those numbers again. Then rounded quarters, and if you just compare Q and Q star, then Q is greater than Q star for first line, but less than Q in the second line, but yeah, still less than Q in the second. Q is less than Q star second line, less than Q star second line, but the last line, okay, again, yeah, it is also less than Q star. So rounded quarter should be, in case of the first line, we need to round up, but for all other cases, we need to round down to get the numbers. And if you add all the numbers, then it is 11. So here, one situation remained. So we need to use di plus, right? And this is pi over square root of ni times ni plus 1. So here, di plus first one, it should be the same, 174 over square root of 4 times 5, which is almost, okay, I write down it as a green one, 174 over square root times 4 times 5, which is the same as 38.9076, and 166 divided by 3 times 4, which is the same as 479201. And in case of the third line, 121 over 2 times 3, it is almost same as 49.3980. And the third one, it is 70 over 1 times 2. It is almost same as 49.4975. And 69 over 1.2 is 48 over 497,908. And if you compare all those numbers, then the first one is the greatest one. So you need to get rid of, you need to give it one seat. So the adjusted seat should be all others are same except the first line. The first line will get 2 seats. So then your method is done. So that's all for the correct video. And again, I'm so sorry about this terrible mistake I had. So sometimes, when I just go to the in front of you, then sometimes I just think that, yes, yeah, I am also a little bit nervous. So I had such a, terrible mistake again. So I'm so sorry about this mistake and hope that this helps you to understand the Hill-Huntington method better, right? Thank you.